So probability is either a number from 0 to 1, a percent from 0% to 100%. Okay, so probability. A number from 0 to 1. Zero, there's no chance of it happening. 1, it's a certainty. Okay, that it will happen. And then we've got that spectrum in between, right? And if you're reading about it, you know, the closer to 0, it's less likely. When you're in the middle, the odds are 50-50, then it's, you know, equally likely that it happens or doesn't happen. Okay? Generally tend to define probability, usually write it as a fraction. So probability, usually written as a fraction, right? So it is a number from 0 to 1, or from 0% to 100%. With probability, you can never give more than 100%. Okay? Or fraction. And the fraction is, again, from 0 to 1, right? But, you know, 1/2, 2/3, 3/4. Probability is the number of favorable outcomes over the total number of outcomes. Okay, so if we're talking about flipping a coin, there are 2 outcomes. Heads or tails. If heads is favorable, it happens 1 out of 2. We can conduct an experiment with the coin. We could toss a coin. It says that in the sections you read, you know, do this, do that. You don't have to do those experiments, right? But they're just there to give you an idea. So that's experimental probability. Okay, so experimental probability and that can only be used for some things. Like, let's say, so they were using tossing tacks, right? I mean, if I toss a tack, what's the probability it comes up, heads up, or you know, pointy end up, or the pointy end is on the table? What's that probability? Right. Okay, no answer, because nobody knows, right? There's no theoretical probability for that. So the only way to do that particular experiment would be to get that probability would be to conduct an experiment. You have to toss a tack, or toss a few hundred of them and then count, right? And do that many, 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 many times, right? We can't program a computer model for it, because again, we don't know, right? Same thing with, let's say you have a cup of coffee, a Starbucks cup, or a cup from the cafeteria, and it's empty because we don't want to spill, but it gets knocked off the table. How could it land? On its side, right side up, or upside down? Which is more likely? Sideways. How do you know? Because you have conducted a number of experiments in your life. You've knocked cups off or seen cups knocked off tables, and you've seen them land. You ever seen a cup stick the landing, like a full cup, just go, you know? Yeah. How often does that happen? Very rarely, right? So you go, whoa, like, you know, what just happened? It's, you know, that doesn't happen that often, right? That's an experimental probability, right? So we would have to conduct an experiment. And then the probability would be the number of favorable over the total. So if I did this 1,000 times and it landed on its side 855 times, the experimental probability would be 855 out of 1,000, which we would then reduce as a fraction. Sometimes, especially with fractions, if you're trying to compare them, it could be difficult. So then you convert the fractions to decimals. You get a decimal between 0 and 1. And if you like percentages, then you multiply that decimal by 100 to give you a percent from 0 to 100%. Right? So percents and decimals are very easy to compare. Fractions with the same denominator are very easy to compare, but fractions often otherwise are not so easy to compare. So, you know, we just want to be aware of what's going on there. There's a little chart in the book that tells you you've lived this long, then this is how much longer you're likely to live, right? Those are called actuarial tables. And they're made by people called actuaries who look at all of the statistics involving that and do some fairly heavy math and number crunching, because that's where the concept of insurance came from, right? they knew that, okay, if you've lived this long, if you've made it this far, you have a pretty good chance of making it another, let's see. If you made it to 55, then you got a chance of living another 22 years, right? You're going to hit like 77. If you made it to 15, which is about where you guys are, then you got a chance of living another 60 years, right? So you'll make it to 75. Okay, but the further along you make it, the greater the chance that you're going to make it further still, right? Because you haven't died yet. So, disease hasn't got you, or an accident, or whatever. Okay. Okay. Well, no, as you get older, your insurance costs go up. Okay, so then it discusses experimental probability, right, which we've just talked about. You conduct an experiment. Then there are some questions. That's 19A. You can leave all those for tomorrow. They've got coin tossing experiments, but with coins, we know what the outcomes are. And the same thing, they got a dice rolling experiment. But with dice, we know what the outcomes are, which brings us to page 474 and sample space. So sample space. Sample space is the set of all possible outcomes. So it's a set. We would use set notation. So it's a set of all possible outcomes. So we list the sample space for toss a coin. What are all the possible outcomes for tossing a coin?
Sideways.
There is no sideways when you toss a coin. Thank you, anyways. If Chris Hadfield was tossed, yes, maybe, but not now. Okay. Coins don't land on their sides. And if they do, we'll smack them down. Okay. So a coin can land. The possible outcomes are heads or tails. What if I toss 2 coins? Okay, wait. Now, are heads and tails equally likely? Yes. Okay, what if I toss 2 coins? What are the possible outcomes? Head, head. Head, tail. Tail, tail. And tail, head. So how many outcomes are there? Are they all equally likely?
Yes.
Okay. Yes, they are. Now, if we'd have said it as 2 heads, 2 tails, or 1 head and 1 tail, then those are no longer equally likely. We've only listed 3 outcomes, right? Because this is 1 head, 1 tail, but this is also 1 head, 1 tail. Okay. So we have to be careful how we list the sample space, right? Or how we discuss this, right? If I said, oh, you toss 2 coins, you get 2 heads, 2 tails, or 1 of each. Are those probabilities equally likely? No. Because the 1 of each could happen this way or this way. Okay. So we need to take that into account when we do a sample space. Okay. And they show you a couple ways. One is with a grid. So actually, I'm going to turn the grid sideways. I don't like the grid. So here's coin 1. Let's make this coin 2, I guess. Go top to bottom. Here's coin 2, here's coin 1, and coin 1 can come up heads or tails. Make a little grid there, and list the outcomes, right? Head, head. Tail, head. Head, tail. And tail, tail. So that's one way to list the outcomes, right? Make a little grid. This works nice if that, yeah, okay. Supposed to be a T. Jeez, everybody's a critic.
Hey, it was the Chinese character, so that's completely different.
And what did it say?
Down. The line was the sign.
Another way to list outcomes. Family of 3 children. What are the possibilities for a family of 3 children?
33.3%.
3 boys? 3 girls?
Boy, girl, boy.
2 boys and a girl, 2 girls and a boy. If we list it that way, 3 boys, 3 girls, 2 of one, 1 of the other, and vice versa, are each of those equally likely? No. Because we know that having 2 boys and a girl can happen how many ways? Well, maybe we don't know, so we need a way to list that, right? We might need a way to enumerate this, in other words, to get the sample space. Now, can we do that with with a table, right? Child 1, child 2, table, with a three-dimensional table, yes, but not with a flat table, right? That's not going to work because all we can do is have two things, right? There's the one and then the other. So I could do child 1, child 2. So a family of 2 children, we could do a little table, very nice. If we want to go beyond that, family of 3 children, we're going to do what's called a tree diagram. So here's the first child, second child, third child. So these are the column headings. A tree diagram basically grows from a root. So there's the root, and we know that if you have the first child, it could be either a boy or a girl. If the first child is a boy, what could the second child be? A boy or a girl. First child's a girl, what could the second child be? Boy or girl. First child's a boy, second child's a boy, what could the third child be? Boy, girl. What if I wanted to do 4 children? We would just put another column on there and we would list, right? So now, in order to list the sample space, we trace each branch of the tree. So what's this branch? Boy, 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 right? And then we just trace each branch and list the outcome. Oops. G. These are G's. Okay, so how many possible 3 children family are there? 8. Are each of these outcomes equally likely? Yes. How could we figure out the probability? Well, we could ask, what's the probability of a boy? So at any of these, the outcomes are always 1/2. So this outcome occurs with a probability of 1/8. How do I get that from a half, a half, and a half? Multiply them together, right? And this probability, and what is it going to add up to? 8 out of 8 or 1, right? So if you've done a tree diagram correctly, you have all the possible outcomes. You traverse the branches of the tree, you can list the probabilities. They have to add up to 1. If they do, you've accounted for everything. If they're more than 1, then you've got too much stuff there, right? You've repeated something. If it's less than 1, then you've left something out. So if I'm going to list the sample space, then it would be boy, boy, boy. Boy, boy, girl. Boy, girl, boy.
Guys, there's only 8.
Yeah, there's only 8. It won't take that one.
Add a 4th child in there.
If I had a 4th child, how many outcomes are there?
32.
32. If I had a 5th child? 64. What's the probability of having 2 boys and 1 girl?
1/6.
No.
What
No.
am I talking about?
No.
No, wait, a quarter.
No, 2 boys and 1.
2 boys and 1 girl.
Oh, okay.
Is this 2 boys and a girl?
No.
Is this?
Yes.
Is this?
Yes.
Oh, I was right.
Is this?
No.
Is this?
Yes.
Oh.
This? Okay, what's the probability of having 2 boys and 1 girl? 3/8. Okay. What do we do with those probabilities? We add them together, right? Okay. Why? Well, you think of it, the easy way to think about it is, well, the girl, there's only 1 girl. She is either the oldest, the middle, or the youngest, right? So there's 3 of those. Yeah, there's 3 places for her to go.
Arsenal turns around. He just ignores us. Just smiles.
We'll get to the square. Because of the
Okay, so that's listing a sample space and then using the sample space to calculate some probabilities, right? So, two-dimensional grids work, but only if there's two things, right? Works very nicely for rolling two dice, right? A pair of dice. But doesn't work so nicely for three dice, right? Okay, so then you move to a tree diagram. Right, which brings us then to theoretical probabilities, which, well, we've just done a theoretical probability here, right? So one way we could have done this as an experiment is just stop people in the hall, said, how many kids in your family? 3. Okay, if they answer 3, then say, how many boys, and just,
What happens if they ask?
just enumerate it by the number of, and then try and work out the probability that way, right? And we know that 2 boys and a girl should occur 3 times more often than all boys or all girls, right? If we just did it, okay, let's do it here. How many people are in a family with 3 children? Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, there's 7 of us. How many have 2 boys and 1 girl? 1, 2, 3, 4, 5. See? So we would say the experimental probability of 2 boys and a girl is 5 out of 7. Right?
Except that that's probably inaccurate.
Well, why is that inaccurate?
Because you don't have enough people to ask.
Don't have enough people, so we'll go next door. We'll ask that class. Will we start to get closer?
Yes.
Okay, and then we'll ask the class on the other side. So what do we need if we're conducting an experiment? What do we need to do? You need a large sample, right? So the larger your sample, the more confident you can be that you're going to get close to, right? Small sample, here we had 5 out of 7. I could do this next door and it would probably be less, right? But what's it eventually going to come out to? It's going to come out to 3 out of 8, which is 0.375, which is 37.5%, right? Again, we can express it 3 different ways, right? Okay, so theoretical probabilities remove that from us when we have cases where we know stuff, right? We know that. However, I was just reading the article the other day on Alberta baby names, and they gave the total number of boys and the total number of girls born. Worked out 51.5% boys and 48.5% girls.
I told you
Okay,
violence.
so it wasn't exactly 50-50. Now the reason I think is because boys do stupid things and kill themselves off at young ages, so nature accommodates for that by creating more of them, so that,
Logic.
Wow.
But that's only my personal
By 10th grade, it should have worked itself
thing.
out.
No. When boys kill themselves, they do it they do it in their 20s when they're really stupid. Okay, complementary events. Okay, so when we're working out the probability of precipitation or something, we say either it rains or it doesn't. So these events are complementary. What would their probabilities have to add up to? 1, because they take into account everything, right? So if I know the probability of rain or precipitation is 0.2, what's the probability that it doesn't rain? 0.8. How do we calculate it? We go 1 minus 0.2. Since we know that these two probabilities, so for complementary events, the probabilities have to add up to 1. So what's the probability of rolling a die and getting a 5? What's the probability of rolling a die and get a 5? 1 out of 6. What is the probability of not getting a 5? This, by the way, is the not getting a 5. Right, 5 out of 6, right? Again, because those probabilities have to add to 1. So the probability of A plus the probability of not A is equal to 1. Okay? If it's given as percent, then it's 100%. That takes us past 19C.
Oh, what?
Using grids to find probabilities. We've already done the trees, so we don't need to do the grids. But the grid again. What you want to do if you let's do a grid. Let's roll the dice. Roll the dice. Okay, we've got die. Okay, we'll do this. We've got the red die and the blue die. I was going to use green, but. But then if you're red, green, colorblind, really, they just look the same, right? So, okay, so the blue. 1, 2, 3, 4, 5. I know. I should have just brought in a table. Well, it's too late for that. Okay, so the red die can come up how? And the blue die can come up how? Now, we could, usually when you do roll a pair of dice, so we could list the outcome, right? Which we could say this is 1-1, and this is 2-1, and this is 3-1, and 4-1, and 5-1. Usually we're interested in the sum. Okay? So let's just go through this, and now I can use green and we'll fill in the sums. So what's this sum? Okay, there's no, yeah.
Bog sweeper.
Oh my.
Okay, so a table or a grid is a very nice way to list the outcomes for a pair of dice, right? Not so good for 3 dice because it's not 3-dimensional, right? I mean, then I would need to do a tree diagram.
Maybe like a.
So how many outcomes are there?
36.
36, right? Because 6 and 6. How many outcomes for 3?
2 times 3. What do you mean, like the sum?
3 die.
Oh,
3 die.
216 outcomes. Yeah, now if we're talking about the sums, how many different sums are there?
12.
I think it's countable.
10.
It's countably
It's
finite.
11. It's 11.
It's 11.
11.
Oh.
It's definitely
Oh,
11.
that's
Alright.
yes.
12 minus 2 plus 1.
What?
Okay, so you can get a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. You throw 1 in there, but you can't get the 1, but that would make 12, so it's 11. Right? Doesn't matter. Or you can just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 sums. Are they all equally likely? No, not at all, right? So, if I want to use a grid to find a probability, what's a probability we could look at? We got,
Why not 8?
we'll just do it. What's the probability of a 7 or 11? Because, that's for the game of craps. 7 or 11. 7 or 11, there's a dice game called craps, right? So, the study of probability started with what? What were they interested in? Gambling, right? Because if you knew the outcomes, right, and it was just, well, what if we have to stop playing at a certain point in time? Then how do we divide out, right? So we need to know who's more likely to win, right? You had this chance. You watch poker on, you ever see late night? You can't help but, you're just rolling around the channels and there's late night poker, right? And they're always giving the percent of winning, right? So they always say, here's this guy's hand and this guy's hand, and they have this percent of winning. What's that based on? Well, it's based on a deck of cards and the possibility, right? The probability of certain cards coming up that would help somebody's hand, right? And you get to the point, at some point, where it's 100% and 0%, right? Because this guy's already won, this guy doesn't know it, right? He has no chance of winning. It doesn't matter what cards come up at this point, this person already has won the game, right? That's 100%, 0%. It's certainty, right? That might be 95-5. In other words, there is one card in the deck that this person can win on, and otherwise they don't, right? And so, sometimes that happens, but not that often. So, what's the probability of a 7 or 11? Okay, so 1, 2. So what we want to do then is let's take a look and let's count. 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 out of 36, which reduces to 2 ninths. Okay. Now, whenever I'm doing probability, I like to list. I'm going to call it the raw probability, right? Just the actual count. It's 8 out of 36. Okay, because that tells everybody that there were 8 out of the 36 possible outcomes, right? So my denominator usually, my first denominator is the total number of things that can happen, total number of outcomes. Then I'll reduce it, right? So okay, that's 2 out of 9. What's the probability of odd or 10? Close.
21 over 36. 21.
Okay, 21. How many of those outcomes are odd? Half. How many of them are even? The other half. They're complementary events, right? You're either odd or even. Complementary events, a sum of 10 or not a sum of 10, right? Complementary events. All right, so we get 20 out of 36, which reduces to
7 out of 12. I actually 7 out of 12.
Now, if I initially just asked you to, well, okay, those are too far apart, but all right, something else. Here, how about this? Probability of doubles or
Triples.
greater than or equal to 10. Probability of doubles or greater than or equal to 10.
12, 36.
Not. Well, you throw. Wait. Let me calculate it first.
No, wait, 11.
Yeah, what is he?
No?
10.
Idiot.
It even speaks like the first time. You must like this probability stuff. Okay, now. All right, you might not be seeing that, right? So let's go through and we'll just okay. So doubles, right? Doubles. Okay, greater than or equal to 10. Let's do that I'll do that with green circle, blue circle.
10, 12, 12.
Greater than or equal to
Oh,
10.
there's 6 doubles. Yeah.
Okay, so how many circles did I make? I made 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I made 12 circles. But wait, you said there were only 10. But I circled 12 things.
But you circled the same thing twice.
What did I count twice?
12.
The 10 and the 12, right? Because, and this even goes further than tomorrow, but it's okay. We're just introducing these concepts. I'm not going to name the concept of that, right? But okay, so doubles are 10 is 10 out of 36, which reduces to 5 out of 18. Okay, now, one thing about leaving the raw probabilities, the 8 out of 36, the 21, the 10, it's very easy to compare 8 and 10 out of 36, right? It's not quite that, it's not that much harder to compare 5 out of 18 and 2 out of 9, because it's very easy to get them both to be 18s, right? But when you start getting 12s and, when you start getting really close stuff like 21 out of 36 and 20 out of 36, and you're comparing 7/12ths to, what's 20 out of 36 reduced to? That'll be 5 out of 9. Yeah, when you're comparing 7/12ths and 5/9ths, how easy is that?
Pretty easy.
Not that easy, right?
Intuitive.
Okay. Yeah, not as intuitive, right? I mean, the 2 out of 9, 5 out of 18, yeah, okay, look, I get 4 out of 18, this is smaller. Okay, but 7/12ths, 5/9ths, but if it was 21 out of 36 and 20 out of 36, it's trivial. Okay, so that's why sort of just listing the raw probabilities and then doing the reduction will always help you out, right? Especially if you have to do a comparison. If not, and if I just ask you to compare these, then just convert them to decimals, right? Just go 7 divided by 12, go 5 divided by 9, which one's bigger? Yes.
For the P odd or 10, shouldn't it be 27, not 21?
You want to come up and show me the 27 of them?
Because that's what I found it. It's like odd or 10.
Odd or 10?
Yeah. Like 27.
Go ahead.
There are 18 odd
There are 18
numbers.
odd numbers.
And there are 3 10s. So where do you get the other 6 of them from?
from the third dimension.
Here, I'll cross off all the odds or tens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. You come cross off the other 6. Luckily, I'm done with this. Okay? Yeah, really. Now, come on. That's an easy thing to count. Okay? So, making a chart or a grid will allow you sometimes to count out the probabilities, right? You don't have to X things out all the time, right? Because you might just count them. Then we move to probabilities of compound events, which is using the word and. So compound events. I think we're now into the next day, right? Yeah, compound events.
Wait, why are we studying?
Because I'm not here tomorrow. So you know what? Let's